Welcome to this lecture on thermal simulation of buildings. That's part of the transient simulation of buildings. And we're going to show today about numerical methods for solving these transient things. One of the methods is the finite difference method, and only the variation, which we call the explicit method, will be talked about here in this lecture for now. So we have several numerical methods, and as I said, the explicit method is one method that we talk about. It has also an implicit variation, which I will refer to our lecture note when you have to read about that. We will give also another video lecture on response factor methods, which you can see separately. The idea of numerical methods is that we discretize the world, so to speak, so time and space will be discretized. And that means that when we take our general partial differential equation that we use to calculate transient heat conduction, well, then all the soft representation with the infinitesimal differentials, delta, we will replace those by finite size steps in time and space. So if we take the space, let's see if we're going to calculate a wall, then the real thickness of the wall we subdivide into volumes of a certain thickness delta x, and we calculate really the conditions only in some node points, grid points in the center of each volume typically. So we have a discretization of the thickness of the wall into delta x's, and we use the number, the letter I to number our volumes of the wall. And likewise for time, we make the differential time step into finite deltas of time, steps in time, and we use the index j to know how far we have progressed to number the things. And also the equation here, the soft deltas were replaced with the soft partial d's were replaced with hard deltas. So we make time steps in time, we make space steps in x, of course, and then we calculate steps in temperature to know where we are to calculate those points. So again, for those points, we can represent a wall for the thickness here with all the points where we calculate things. And as we march forward in time, we come up along the j-axis up here, also in discrete number of time steps. That's again repeated how we do that. And we have the indexes to know where we are. So always we calculate unknown temperatures in the future based on known knowledge from the previous step, and also in the beginning when we start the whole condition in time level 0, we have to have an initial condition to start from in the first place. So again, I just repeat our general partial differential equation for the temperature development, because this is the equation that we now represent in a difference form. So these differences here, the partials are made into differences. So we have changes in temperature from time level j to time level j plus 1 at the same point I. And this we take per time per delta t. For the space discretization, we look to neighbor temperatures. So these are the neighbors to the center point and the neighbor to the right. And here is the contribution of heat that comes to the center point from the neighbor that were to the left. And all this is discretized using delta x squared in the denominator. This we can do because we have the thermal diffusivity in front of it as our material property. Time step we have talked about already, but in this equation we'll use the time step also in another form where we talk, like we've talked previously in the course, about Fourier representation of time. That's dimensionless time, but here we use it as a Fourier delta. So the time step in a dimensionless form, we have to start with a time step, but to make it dimensionless, we should divide by something which is space squared. So that's delta x, our space steps, delta x we take, and we multiply with the thermal property of the material, the thermal diffusivity. Then we get dimensionless time steps. So using that definition of Fourier, well, then we can clean up our equation a little bit in such a way that we try to isolate the new temperature in our central point based on all the other temperatures we have from the previous time step. And in cleaning up, I multiply with delta t. I gather all my information about previous values from the known values for the temperature in the center and all such things. And doing that, then I can isolate the temperature as I intended, and I also inserted the definition of Fourier time step as I just talked about. Well, let me just shift back because important is that the value I had for the temperature in the center in one time level, that it has a positive or at least not a negative correlation with what the same temperature becomes at the next time step. That means that the bracket before here should not be negative. And if 1 minus 2 times Fourier should not be negative, well, that leads to saying that Fourier must be, as this slide says, less than 0.5. And looking to the definition of Fourier time step, well, then delta t must be less than these values here. So there is a limit to how big delta t, the time step, can be. And that means that with such a limit, well, we cannot calculate too fast. So some calculations may take a little bit long. So the explicit method can be a little bit slow, but it's very easy to understand, and it's a very good introduction to the numerical method. Also, I should say that if we are concerned about this, we can indeed actually increase delta t if also we increase delta x, so we make the whole discretization more rough. Then we can have more rough calculations, but then it possibly might not be as accurate. So those are the things we can mingle with in numerical simulations. Stability is the issue that we are concerned with for the critical value for the Fourier. So if Fourier is less than 0.5, as the previous slide says, for instance here 0.48, well then the points show what our numerical solutions to what the solid lines have as an analytical solution in a certain case. And that looks quite nice. But if the Fourier would try just slightly over 0.5, well then we have instability. And this you can try for yourself. In the example I'll show you soon, you can try to work on with that and try to change the Fourier number when you try it. And then you see what it really means with instability. You get sometimes very absurd oscillations in the results. Now, the example I'm going to show, yes, it is a wall. I reuse a little bit the figure from before. A wall with these properties here, thermal conductivity, density, and specific heat, such that I can calculate the thermal diffusivity. The whole wall is 5 centimeters wide, and I use a discretization of 1 centimeter. Initially, I have all the points, and initially down here, they are at 10 degrees centigrade. And then suddenly, when we begin the calculation, the boundary temperatures are increased to 20 degrees centigrade for all time levels onwards at the boundaries. We should determine the critical time step, of course, because we have to, and then we should calculate the temperatures as they develop. I have to insert where my wall on this level here. So here are the boundaries, left and right boundaries, and then I insert this numbering of the elements where I calculate. So let's try now to move to the whiteboard over here, where I will continue the calculation. So in order to do so, okay, sorry, camera guy, can you come back, because there's one point I need to show. I need it here on this. There's the solution, and I introduced already the properties for the materials of thermal diffusivity we can calculate. But then we should calculate the critical time step, and that comes to 500 seconds, because I need to know how quickly I can move forward in time. But that means also that the Fourier number is exactly 0.5. So we're working on the limit for stability. So let's see how that goes when we insert it in our formula over here. So now we can move to the whiteboard, because I have prepared the situation of a starting situation with 10 degrees centigrade, and then I can edit here that at the surfaces, suddenly the temperature will increase to 20 degrees. And then let's see how the things develop. This is my wall. I have to calculate for 4 intermediate points in the wall. But since the wall is symmetrical, actually I can, let's say, cheat a little bit by calculating only until the symmetry line in the middle. So what I'll do, I use my formula, and to calculate this temperature here in the next time step, or the first time step into the field, then I should take half times the value to the left, plus 0 times the value to the bottom, that is how our formula came up, plus half times the value to the left. And that gives me here 15 degrees. And when I calculate the next temperature here, half times 10, 0 times 10, plus half times 10, then I get 10 degrees here. Then I'm done, because now I can copy it, but I'm going to use it, so I just make a replication of the value I have over here. Now I can continue. So when I calculate the value up here, I get, again, half times this, 0 times that, half times that, and that gives me 15 up here. That may use a little bit decimal, but that doesn't change. Up here, half times 15 and so forth, the result becomes 12.5. So now things are moving over here. Let me just, for the continuation, because I'm going to look to the right, I'll repeat what I just had here. I continue, half times 20, 0 times 15, half times 20 and a half. That gives me, in this place here, 16.25. And now I get half times 15, 0 times 12 and a half, plus half times 12 and a half. And this comes to, I think, 13.75 degrees centigrade. And so you can move forward. So it calculates in a stable way. It doesn't go absurd, but we get a little bit, some peculiar bumps, 15, and then it remains at 15. And that was because we were calculating just at the limit for stability with the Fourier number equals 0.5. But you can try now for yourself to use smaller time steps. Then you can see probably a more smooth development as things go forward. You can also try to increase delta t to a value larger than 500 seconds, and then you'll probably see that the results go, let me call it, absurd. So try this for yourself. This was at least an attempt to show to you to work like a computer, but you can do it with pen and paper or a whiteboard as I did, and actually that gives a very good introduction to getting a feeling of how a computer works in such numerical simulations. So I hope you enjoyed it. I hope you'll try it for yourself, and to see you and listen to how it goes. Thank you for now.